Hi, I'm Dr. T, and welcome to my office. Since time immemorial, people have been trying to list all of the known elements. And of course, looking back at the list from the alchemists, it does make a modern chemist kind of snicker, seeing things on there that are totally not elements at all. But this is a reasonable goal. It's nice to, list what you know and know what you know. So as time progresses, we start learning more about the elements. For starters, sorting out the ones that aren't elements and actually having the ones that really are. But as the beginning of the 19th century dawns, we start having this rather interesting ability. We start looking at the relative mass of the atoms. This whole atom theory stuff is pretty new, and we're starting to get this idea that these elements have a mass to them that is dependent on what the element is. Typically, masses at this time are measured relative to hydrogen. So we can say, hey, carbon's 12 times heavier than hydrogen. Today, we still do the same thing, although we no longer directly link it to hydrogen. We use the unit Dalton, which is directly linked to the mass of a carbon atom. Now, with this, we then started noticing an interesting pattern because, hey, if you now know the relative mass, you might as well list them in order. We then started noticing this repeating pattern. The chemical properties of our elements actually, kind of repeated. There were things like fluorine, chlorine, bromine, and iodine that all had very similar properties to them. And if you started putting them on a list, it kind of, repeated. So now the next goal was to start taking this list and making it into some kind of table, something that would allow us to look at this repeating motif for the elements. In comes, in the mid-19th century, a gentleman by the name of Mendeleev. And he's a Russian peasant whose mother strived and really sacrificed to put him through college. He becomes a chemist. And he gets this idea that is definitely not original to him, but he kind of, takes it the next step further. He's going to take the elements, he's going to put everything he knows about them onto cards and start shuffling the cards and tries to make a reasonably ordered deck. Now, he takes the next leap that is, in some respects, entirely obvious and in some respects completely counterintuitive. He goes, you know what, we've discovered a lot of elements. Maybe we haven't discovered all of them. If we go back 20 years, we wouldn't have several of these. So maybe in the next 20 or 30 years, we'll discover a whole lot more. So he creates a table of all known elements, and it has gaps in it. But by the way he's able to order them, he's actually able to make some predictions. Because remember, the chemical and physical properties of these things actually do tend to have a repeating pattern. And so he comes up with an element. He says, hey, this element is going to be kind of a silvery, grayish color. It's going to have a melting point with this range. We just haven't discovered it yet. And the reception is between, who cares? I didn't read it because who is this guy? And, haha, look at this wacko in Russia. He's so stupid he makes a table of all known elements and has holes in it. Now, a few years pass, and then it's realized that, oh wait, there's this newly discovered element, germanium. Oh, it matches this Mendeleev's dude's predictions, like, perfectly. Within, like, about 2% for a lot of the properties. Now, everyone stop laughing. You predict the future, people pay attention. And so now this then evolves into our modern periodic table. What we now see on the wall of every chemistry classroom doesn't actually exist until around the 1960s. It comes in a couple of different flavors. There's definitely some cool old ones, but the modern one we get in the 1960s in its kind of final form. So in looking at the modern periodic table, we can look at a couple of key features. For starters, it's divided into rows and columns. The rows are called periods. The columns are called groups or families, typically groups. Elements in the same group are going to have similar chemical properties. So if you look at fluorine, chlorine, bromine, iodine, as I mentioned earlier, those have similar chemical properties. They are all in the same column. The last column on the right-hand side, the noble gases, they all have similar chemical properties. They don't do much. They just kind of, are there. Hence their name. They're like stuck-up nobles that don't actually do anything. And thus you can look at any element on there and you can assume the one above or below it is going to have fairly similar chemical properties. Not identical, but similar. Now, the periods, as you go down, those are going to go down and the atoms are going to start getting bigger and a couple other properties with the periods, although those are usually of somewhat less emphasis to us than the groups. Now, with our periodic table, we'll see that it has a couple of interesting lumps and bumps, and these patterns actually reflect the outer layer of electrons on these elements. The outer layer of electrons is known as the valence shell, and the valence shell is the electrons that are going to be interacting with the rest of the world, and thus those are really where the interesting stuff takes place. Typically, a periodic table is broken into 4 kind of large squarish regions. Although I will caveat here, hydrogen and helium kind of belong in a couple of different spots. So while you will always see them in their usual location, what I'm about ready to say does have a little bit of quirks when it comes to hydrogen and helium. The 2 groups on the far left, those are governed by electrons that are buzzing around in the outer valence shell, more or less in a kind of a spherical shape. And there's usually not very many, 1 or 2 electrons on that outermost shell. And we generally call this the S block. And these will have names such as the first group is the alkaline metals, the second group is the alkaline earth metals. When you see the word earth in a descriptive for an element, it means it's something that's commonly found in minerals. Then you'll notice on the other side of the periodic table, you have another large square with helium kind of sticking above it. We call that the P block because this not only has electrons that are buzzing around in this kind of spherical shape, these shapes, by the way, are what are called orbitals. But they also have other electrons buzzing around in what are basically kind of dumbbell-shaped orbitals. And thus these are governed by the electrons that typically are doing that kind of dumbbell-shaped thing. And thus we call that the P block. That kind of dip in the middle, these are a little bit more elaborate orbitals, usually not on the true outside. We call these guys d orbitals, and we call that the D block. This also gets known as the transition metals because it's transitioning from the left side of the periodic table over onto the right side, and their chemical properties are actually relatively similar to each other. That dip in the bottom will go by a couple of different names. Those are, once again, being governed at least somewhat by what we call f orbitals, or which is rather complicated orbital structures that are usually not, once again, on the actual outside. And these all have very similar chemistries to them. They're sometimes referred to as the lanthanides and actinides. It's probably the more technical, more popular name for the first 2 elements in those 2 rows. You'll also hear it called by its older name, the rare earth metals, although the term rare is a little bit misleading, as some of them are not all that rare. Now, no discussion of the periodic table would be complete without looking at 3 other general regions on the periodic table. If you look at the periodic table and you look at the left-hand 2/3 of it, these are what we will call metals. And to be clear, this is not kind of a binary decision. This is actually kind of a continuum. Typically, those more left and down are going to be more metallic. So these are going to be things that have properties that what we would normally consider those to be metals. Shiny, ductile, which means you can pull them the wires. Malleable, you can beat them into sheets. Good conductors of electricity and heat. On the top right-hand side, these are nonmetals. These are going to be ones that are basically the opposite of metals. They're going to be brittle, they're going to be dull, they're going to be good insulators. And right on kind of the border, we have the metalloids, which are, kind of in between the 2 and don't fit neatly into either category. Now, I will point out there's a little bit of controversy whether or not you should really be dividing those into 3 distinct groups, because in reality, once again, nature doesn't have boxes. Nature does what nature does, and it's more of a continuum between those properties. But you will notice a series of properties for elements going by this kind of lower left, upper right hand diagonal, where as you move one way or the other, they get similar properties accumulating in one direction versus the other. So with that said, have a wonderful day.